with the sound. Can you? Okay.
Anton, do you have? Is there any chance that you have maybe two devices with sounds activated?
Sorry, say it again.
Is it possible that you have two devices with sounds activated?
No, I mean, I have just this one device.
Okay.
But I can mute here the.
Because, or maybe it's because between you and Cornelia. Like yeah, I think it's better. So I think that only one of you can have the mic open at a time.
Yeah, I think so.
Ja, dann mache ich das. Okay. Now I can probably hear you again.
Yeah, I think it's better now.
Ich verstehe jetzt, ich höre jetzt gar niemand.
Du hörst niemanden?
Nee. Nee, ich höre jetzt gar nichts. Das du vielleicht einschalten bei dir.
Eingeschaltet.
Ah, jetzt höre ich es.
Is there a typo in the name of Cornelia?
Pokaliuk. Oh, yes. But this will be fixed. Yeah, yeah.
Okay.
Cornelia.
Part of the fixation
It's a random mutation.
Yeah, this was just a mutation, exactly. You can write in your slides.
Yes, yes.
What are you using, Anton? Are you using iPad?
Yes, yes.
I see.
Yes. So
I was thinking that I don't have to think about such things anymore, but now I was just saying it's not clear if the next term is still online.
Yeah, yeah.
Yeah.
No, in here it hopefully will not be online.
Mm-hmm.
I did a hybrid format all the time.
Yes?
Yes, yes.
With some students.
Right. Some students in the lecture hall.
I see. And then you were live streaming it.
Yes, yes, yes.
Hi, Anton. This is Frank. Did the
Hi,
students?
Frank.
Hi.
Hi, Frank.
Did the students have to register beforehand, so that they, because of limited numbers, or not?
No, no. I think
okay.
The organizers know this better, but I think it's quite open, right? It's open.
No, for your lectures. I mean, your hybrid lectures.
For my lecture, yes. Every week they had to.
Okay.
They had to lecture. They were invited to register.
Wonderful.
Yeah, people are still coming, but I think nonetheless we will start.
Okay.
This is also an experience from the lecture that you should maybe not wait for everybody because people will come all the time. So welcome everybody to this last session of the One World Probability Seminar before the summer break. And fittingly to this last session, we have today the topic is fixation of slightly beneficial alleles from a backward and a forward perspective. And we are happy to have Anton Wackolbinger and Cornelia Pokaliuk from Frankfurt. And so they will both give the talk. And I think you, Anton, will start.
Yes, and we will.
Green is yours.
Thank you. We will do a ping-pong situation in both hours. Both Cornelia and I will speak, and I will start with an introduction. The second part will be by Cornelia on moderately strong selection, a forward perspective. The third part will be again given by me, moderately weak selection, a backward perspective. And the outlook will be heavy-tailed offspring distributions by Cornelia. Before I start, I would like to thank the organizers, Nina and Julien and all of you who are present. It's a great pleasure to be with you. Haldane's formula. This is a, I would say, rough and ready rule in population genetics for the fixation probability of a slightly advantageous allele, which at some time enters in the population and may or may not establish there. And Haldane in 1927 observed that the fixation probability is approximately the selective advantage times 2, actually. That's Haldane's formula, times 2. We will see what's going on. Okay, this is Haldane, a very remarkable personality, as you can find out when you look into his biography, and a colorful person, actually. One of the 3 big people in population genetics: Fisher, Wright, and Haldane. Lindival and Patwa, they write in a survey paper, the most widely known result regarding the fixation probability is Haldane's celebrated approximation obtained for weak selection using a discrete time branching process. Haldane demonstrated that the probability of ultimate fixation of an advantageous allele is given by this formula, which I just told you, when the allele is initially present as a single copy in a large population. We may then later debate what this weak selection actually means, right? But for the moment, let's leave it like this. Well, what did Haldane do? He looked, just as Fisher did, he looked at the approximation of the Wright-Fisher model for large population size. And then, you know that in the Wright-Fisher model, we have this choice of the mother by throwing a die. And so this is a multinomial, and the offspring sizes of each individual are then binomial NN, and that leads to the Poisson, and he computed with Poisson distribution, right? That's what I just said. The parental graph in the Wright-Fisher model, which is the links between the daughter generation and the mother generation, is that every individual in the daughter generation chooses her mother, right? And these choices are done by IID uniform picks. So the number of daughters for each of those individuals in the mother generation is binomial, and the limit is Poisson. And if we have a slightly beneficial mutant, then the offspring is on average not 1 as it is in the binomial, but it's on average 1 plus S. And so Haldane could tie in with the results of Galton and Watson. And actually, I should not forget, because one of our organizers is French, and not only, therefore, right, also of PNMA, who discovered these things quite a bit earlier than Galton and Watson, but probably Haldane was not aware that he also built on work of PNMA, because that was discovered in the society, in the community, only in the 60s of the last century. Anyway, the fact is that the extinction probability of a Galton-Watson PNMA process is the smallest solution of this fixed point equation, where phi is the generating function of the offspring distribution. Now, for Poisson 1 plus S, we have this form of the generating function, and this, if 1 plus S is now close to 1, right, then the thing looks like, oh, I mean, we have here this the diagonal, and we have a slightly supercritical thing, which is here nearly slope 1, right? But we can expand, and an expansion up to second order gives here this fixation probability, because here this is the extinction probability, right? Downstairs here, that's the extinction probability, and this upstairs here, this little bit, is the fixation probability pi. Okay, now a few years later, in 38, Kolmogorov looked into these things. He was aware of Fischer's work. Probably he did not quote Haldane's work in this wonderful little paper, which is so nice to read. Kolmogorov here in German, right? I mean, Kolmogorov zur Lösung einer biologischen Aufgabe. This is solving a biological task. And you may read here either in Russian, we are a one world seminar, right? Or in German, which is so nice. I will celebrate this here, right? This omega is just m minus 1. That's the S, right? And the K0 is the initial number. In our situation, the K0 equals 1, right? And the P0 is the extinction probability. So 1 minus P0 is the pi, right? So, and he says, I will translate it into English. Is the initial number small in with respect to this omega? Then there follows this asymptotics. And now comes in bold letters. Die Wahrscheinlichkeit zu überleben, der unbegrenzten Vermehrung, that's what he calls it, the growth, unlimited growth, right, of the offspring ist also dem, and now this word was just destroyed in the scan, but Cornelia, who very well speaks Russian, told me that this is die Auslesewahrscheinlichkeit. Die Auslesewahrscheinlichkeit, which is the Auslesekoeffizient, der Auslesekoeffizient. Auslesekoeffizient. Right, but it's still, I had to complete it because it's here Auslesekoeffizienten, right? And that's the coefficient of selection, right? So this omega is just the S, right? And the P here, that's the second factorial moment. Factorial moment, which is just the V minus the the squared mu. No, V plus minus the squared mu. Or the M, you like one, the M, the mean number, plus m squared. I hope I get the signs right. But anyway, the m plus m squared is small, so because both are close to 1, and therefore we have Haldane's asymptotics. Now let me give up for later a warm up and look at Haldane's formula in the Moran model. In the Moran model, we have many of you will know this, a graph, the Moran graph. We have here 1 up to n, and the time is continuous. And every individual numbered by 1 up to n shoots an arrow, and this arrow is shot at rate gamma half. That's the rate of shooting arrows. And whenever it shoots the arrow, say from I to A prime, then it puts an offspring at I prime, and the individual which before was at I prime is killed, right? And this is at rate, the arrows are shot at rate gamma half, and where they are shot, that's just uniform. So that's rate gamma half. And the individuals of beneficial type, they are privileged. They can shoot their arrows at rate gamma half plus S, right? And now this is a birth-death process concerning the number of beneficial type individuals. The increase it's linear, right? It's but it's also proportional to whom you can transform from a before other type to your type. So we have here this x times n minus x, and the decrease is, of course, it's going up in tendency. The decrease has only this gamma half xt n times xt. Now, I think Pat Moran invented this model in the 60s because one can do so nice calculations with it. It's just fun to state here that up to a random time change, this is nothing but a random walk with the up to down odds, right? You have up, you have 2s plus gamma, and down you have gamma. And I would say, right, the embedded chain is a discrete Markov chain, is this random walk. And we all know from our elementary stochastics experiences, that's easy, right? That's a geometric thing which enters here. That's the solution of the first step decomposition, and the pi n, if you insert, gives this at first sight a little bit involved formula, but we will see that this, I mean, it's explicit, that's wonderful, right? And when S tends in a suitable way to 0 and n tends to infinity, which is our objective also in more complicated models of population genetics, then this has a wonderful asymptotics. Now, let me still dwell on the Moran model and give you also a backward perspective, because this was a forward perspective. We just did a first step decomposition, and we invoked our elementary stochastics knowledge, and things are fine. Now, there is a backward perspective, and that's the famous Neuhauser-Krohn ancestral selection graph. Let me once again do my little sketch of the Moran graph. Here is the time running in forward direction, and we look now on the genealogy of some individual I, right? Or maybe more individuals. How is that tracing the lines backward? Well, you see, there are these additional arrows. I mean, if we would not have this selection business, then this would just be the good old coalescent, right? Two lineages here, they would coalesce at rate gamma, because we have this gamma half in both directions, right? So this would be the coalescence. But then there come these privileged arrows, which come at rate s, and if they come, you don't know whether this arrow must be followed or not, right? If there is such a privileged arrow, it could come from a selective advantageous individual, or it could come from a wild type individual. You don't know this. And therefore, the nice idea of Neuhauser and Krohn, which was around also in particle systems at that time, also biased Volta model and things like that, this was to go in both directions, also to follow this thing here, to branch whenever such a privileged arrow, some selective arrow, those ones that come at rate s, those purple guys come at rate s, you go and branch, right? And the potential ancestral lineages, they perform a branching coalescing process. And the number of potential ancestral lineages is a birth-death process with this death rate and this birth rate, right? Now, it's a nice observation. We learned this from a paper by Fernando Cordero from Bielefeld, who investigated a related model, but forward in time a few years ago. Nothing to do with the ancestral selection graph, but these things also appeared. If you have a birth-death process with this death rate and this birth rate, then it has a nice equilibrium. And the equilibrium is binomially distributed with parameter n and this success probability, but conditioned to be non-zero, right? Because of the birth, you cannot hit zero. Well, that's an easy homework to look at the reversibility conditions. That's a reversible equilibrium for these birth and death rates. But now there is a very crucial observation which will play a role later on, right? If we ask, is at some late time, has there a fixation happened by an early mutant? Then we can follow this line counting process of the potential ancestral lineages, right? This birth and death process. We might start with a capital N, right? We might trace back all the potential ancestral lineages from some late time t and look what does this number of potential lineages do? Well, there is this quadratic term which pushes the thing down. And let me just make a logo, a sketch. What does this thing do? It goes down, it goes up, it goes down. And after a long time, this is large, it has reached its equilibrium virtually, right? So the number of lineages, number of potential lineages, which we have here, this is roughly the equilibrium state of this line counting process. And somewhere here sits the one mutant, right? This one mutant, let me maybe draw this in another color. This thing here is the, this is, I could throw it in green. So that's this thing here. green. And somewhere in here sits this one mutant, right? Things are all exchangeable here. And there was this one mutant a long time ago, large time interval. And the question is this thing, is this one mutant among the potential ancestors? Is this one mutant among the potential ancestors or not? If it's among the potential ancestors, then eventually, because there will have been bottlenecks here in the ASG, the beneficial type will penetrate into everybody at late time. So let me modify this a little bit. Let me just do as if this, let me pretend that this captured this one initial guy, then everything will be red at this late time, right? So everything will be red. So it's just a question, does this random set of potential ancestors a long time ago, does this contain this one mutant or not? And the probability for this is simply enough. It's just the expected ratio of the green number to n, right? Because that's the probability that a random red individual falls into this set of potential ancestors. If you do the calculation, which is easy, then you come to the same fixation probability which we had by the forward argument, right? Now let me end this first part of the introduction by stating that this equilibrium, this fixation probability in the Moran model, which we obtained in two different ways, right, by the forward perspective and the backward perspective, has various regimes. So when S is constant as n tends to infinity, then this converges to, well, we can say Haldane's formula, because the gamma is the analog of the offspring variance here per generation. So that's nice. Moderate selection, where S is a fractional reciprocal power of the n. This is again nice. The Haldane asymptotics works, but weak selection in the, well, let's say, sense of, as we understand it, when the Sn is approximate, is asymptotically equal to a multiple of 1 over n. This is what is familiar from the diffusion limit, right? Then enters another thing here, the exponential of that guy, and that's Kimura's formula, right? But which apparently was known to write also already. Now, let's go to the main topic of this afternoon, which is Cannings models. Cannings models are generalizations of the classical Wright-Fisher model. And you see, in the Wright-Fisher model, this was a multinomial vector. This was a multinomial vector. But here, this vector is only required to be exchangeable. That was the idea of Chris Cannings also in the 60s. And of course, they have to sum to 1. And they are IID as a n-tuple from generation to generation. And in our entire talk, we will focus on a certain nice class of Cannings models, namely Cannings models admitting a paint box representation, right? That is mixed multinomials, right? So we have a two-stage experiment. First, we assign to our individuals random reproductive weights, if you like, in an exchangeable way. Those weights are non-negative and sum to 1, and that we do from generation to generation, right? And this is, so to speak, the role of the randomness in the reproduction, right? And on top of this will come the selection, right? Because we again may color one guy in red, and this guy, what will it get? We will see in a minute. But let me just dwell on the neutral thing for a second. This is mixed multinomial, as we said already. And the basic examples are the Wright-Fisher model, where all these weights are just 1 over n, right? And you could also have Dirichlet weights. These are also a prominent class of weights. In fact, this was one of the motivations a few years ago, where we were faced in another context with a similar situation. Maybe we'll comment on that later in more detail. This is the logo which I want to keep you in mind. Here are those weights, right? And in order to have more space and in order to play with the selection, we look at the square, right? So this is here 0 to 1 and 0 to 1, the unit square. And we have these stripes which have area, well, just wi, right? So the stripe which belongs to the individual I has this stripe wi. And now how to bring in selection from one generation to the next? Well, think of in generation G minus 1 as a number of K wild type individuals being given. Then for good reasons, in order to make the calculations easier, we now play in the other direction. Doesn't affect the limits. The weight of the wild type individuals is decreased by this factor 1 minus Sn, whereas the weight of the beneficial individuals is 1. And so we have here this logo. The K beneficial, the K wild type individuals here, those K wild type individuals, they have a reduced weight, right? These are the wild type. And the rest, they have weight 1. And how do we now generate the step from this generation to the next? Well, in the same conceptual way as in the Wright-Fisher model. We throw uniforms and, for instance, the number and for instance, the mother of the first individual in the daughter generation is the stripe where the first uniform lands. But mind, these uniforms are thrown into the colored region. So to hit a beneficial individual's stripe is in tendency higher than to hit a wild type individual's stripe, right? And we will do much more with this model, and we will construct the pendant to the Neuhauser-Krohn ancestral selection graph also in this time discrete model, which will allow us to proceed further. But now it's time to hand over to Cornelia. Yeah, I will have to. Should I stop? No, I cannot. Well, I can. Neue Freigabe. Freigabe für mehrere Teilnehmer.
Anton, can you try stop sharing?
Ah, stop sharing.
Yeah.
Stop sharing. Yes.
And now Cornelia can share.
Yes.
Okay. Now you can hear me, yeah? Yeah, okay. So we will consider the Haldane asymptotic in the regime of moderate selection. That is, we assume that Sn is proportional to n to the power of minus b for some b between 0 and 1. Yeah, we want to consider two regimes. In one regime, we will see that the neutral genealogies, they lie in the domain of attraction of a Klingman coalescent. And for these kind of paint boxes, so these paint boxes, we consider the case of moderately strong selection, that is B between 0 and a half. And in this case, we will use the forwards approach, that is a coupling with branching processes to show that Haldane's formula in fact gives the right asymptotics. This is the part I will talk now about. And then in the third part of the talk, we will consider the regime of moderately weak selection, where B is between 1.5 and 1. So for 1, we are close to the regime of weak selection, where Sn scales as a constant and divided by n. And in this regime, we will use a backwards approach, so this ancestor selection process to show Haldane's formula. And then in the fourth part, we will consider paint boxes such that the neutral genealogies are in the domain of attraction of a beta coalescent, and we will see what with the fixation probability happens in this regime. Okay, we start with now with a case of moderately strong selection. So B is between 0 and a half. So for B equal to 0, we have a constant selection. Yeah, it does not scale with that. So we assume B is between 0 and a half. And remember, we had these random paint boxes that were a mass partition of 1 that are exchangeable. And according to this paint boxes, the children in the next generation, so we give, but according to these paint boxes, we give the parents weights with which probability they are drawn. And in the next generation, then the children choose these parents according to these probabilities. And they do this independently so that we have these multinomial draws. And the biological motivation why these kind of paint boxes are reasonable to consider are seasonal reproduction cycles. So assume we have a number of parents at the beginning of a season. And these parents produce during the season a large number of offspring, Y1 to Yn. But only to the next generation, because it's winter and, for example, the mosquitoes die and only the eggs survive, only n of these offspring will survive to the next generation. And now we assume that these parents, they are all of the same fit type. So no one of this is fitter than the other. So in fact, we choose these children randomly among all offspring. And if the number of offspring is very, very large, then in fact, drawing with or without replacement is in fact approximately the same. And therefore, the probability that the ith child is an offspring of the jth parent is equal or approximately equal to Yj divided by the total number of offspring. And this is how we next will define our weights. And these we call them Dirichlet type weights. And I just want to say that similar Cannings models with sampling without replacement, so where we don't assume that we in fact put this offspring back, have been considered by Schweinsberg, and then models where one adds selection and notation has been considered by Anton and many co-authors. Okay, so it's for this regime of moderately strong selection, we assume that our weights are constructed as follows. So in each generation, we draw independently and random variables that are distributed according to the same distribution by, and these are almost surely larger than 0. And now we can in fact assume that without loss of generality, the expectation of these random variables are 1, because if I divide here by the expectation and here by the expectation, then the weights do not change. Therefore, we will, in the following, we will always make the assumption that the expectation of y is equal to 1. Okay, and these kind of models without selection have recently been studied by Thierry Hülle and Martin Möhle. And they characterize, so if Zn is a pair coalescent probability, so I take 2 individuals and I asked with which probability these 2 individuals have the same parents, so I can choose one of the n parents and they have to choose the same parent. Then if I assume that the second moment of the y's is bounded, then if I now rescale so I can, I have my Cannings model and I can construct the answer process of this Cannings model. We are not in the selection, this is just a neutral coalescent where the lines are merging. If I scale time with 1 over Cn, then this process converges for each sample size n to a Kingman coalescent. And it is it's in the domain of attraction of the Kingman coalescent. And in this regime, in fact, we want to show Haldane's asymptotic. So let ZG here now, in Anton's talk, this was XG, now it's ZG, is a number of beneficial individuals in this Cannings process with these theoretically typed paint boxes. But we now add selection, as Anton has explained. So we decrease the weights of the beneficial of the Y-type individuals by this factor 1 over Sn. And now we assume that Y has not only a second moment, but we assume that it has even exponential moments, an exponential moment for some h larger than 0. We assume, as I said, moderately weak, strong selection, so B is between 0 and 0.5, and we start with a single beneficial individual. And now if you set rho squared equal to n squared times the second moment of these weights, and we denote by T fixation probability of the neutral or the beneficial type, then the probability that the beneficial types is asymptotically equal to 2Sn divided by rho squared. And this rho squared here is in fact the asymptotically equal to the offspring variance of the individuals. This one, yeah, so so if we take a parent that is so in fact it's not important how many beneficial parents we have because it just gives you a factor Sn. So we take, for example, the first parent and we ask how many offspring it has. It is a binomial sampling because we have n individuals, and we ask if these individuals will pick the first parent as a parent. And so the offspring variance is just the variance of this binomial distribution, and these downscaled weights, this gives only a factor of 1 over 1 minus Sn. So in fact, this is asymptotically equal to the variance of a binomial with parameter n and W1, and this then by the law of total variance, we want to show that this is asymptotically equal to rho squared. And this rho squared, which was a limit of this this expression here, is in fact equal to the second moment of y, because so we can write this expectation as y squared divided by the total offspring number divided squared. And now by law of large number or central limit theorem reasoning, here we have just an n squared, so this is cancelling here, and it's only remaining this second moment of y.
Sorry, if all y's have the same distribution.
I said then in theorem 1, we assume
what is S? What is S?
Y has an exponential moment for some h larger than 0. But we think that in fact this condition can be at least in some cases relaxed. So for example, if we assume that y has a Pareto tail, that is the tail is decreasing like y to the power of some alpha minus alpha times some slowly varying function, then if alpha is smaller, larger or equal than 4, then still the claim of theorem 1 holds. So now I want to give a sketch of the proof of theorem 1, and really this intuition that initially in a population the beneficial allele spreads are like a supercritical branching process, because in the beginning the individuals do not interfere, compete with each other. One really can realize this intuition.
So that if all y is the same distribution, what is
can
S?
be iteratively given or followed as follows. So
Oh,
assume
Cornelia,
that
there's a question
generation
what
G
S
minus 1, we have k number of beneficial individuals, and we number now these beneficial individuals by 1 to k. Then given in generation G minus 1, the parents have the weights W1 to Wn, then the number of beneficial individuals in the next generation is a binomial sampling, sampling of this parameter n, because I have n children that choose their parents. And the probability to choose a beneficial parent is now the sum of the weights of the beneficial individuals divided by the total weight, and the total weight is now the sum of the weight of the beneficial parents plus 1 minus s, because we scale down the weight of the wild-type individuals by the factor 1 minus s plus the weight of the wild-type individuals. Okay, and now we want to approximate this process from above by a branching process and from below. And in fact, we want to do this only for a certain time or until we reach a certain level. So this level n to the power of b plus delta. So so the claim is that we can couple the forward process with a Gordon-Watson process until we either go extinct, so that we don't have any beneficial individuals anymore, or we reach this, in fact, still quite small level n to the power of b plus delta. So b is smaller than 1, and we choose delta such as b plus delta is smaller than a half. So in comparison to n, this is very, very small number still. Yeah. And the claim is that we reach this level with probability 2Sn divided by rho squared plus some smaller order terms. And how we do this? So what we do is that we couple as before this the binomial random variable with a Poisson random variable, and the idea is that that this is really should work is because we for this wi wi so each wi is equal to yi divided by the sum of all yj's. And now we have k of them. So we have the sum of these yi's and we divide by the total sum, but not again by the law of large numbers, and we assume that the expectation of this yi's is 1. We have here, in fact, just an n. And what we have here in the denominator is, in fact, at the beginning, when the number of beneficial individuals is small, we have almost only bi-type individuals. So in fact, this factor here is very small, and we have in fact here approximately the sum of all wi's times 1 minus n, because they are all, almost all, they are scaled down by this factor 1 minus n. So what we have here is the sum divided by n times 1 over 1 minus Sn. So then here this n cancels, and we have Poisson approximately with this parameter. Yeah, and then in fact this gives a coupling from above, is that what one can do is, or what we do is that for each beneficial individual, we ask separately, for each child, we ask separately, will your parent be beneficial or not? And such a Bernoulli random variable, one can couple with a Poisson random variable if the probability of failure for the Poisson random variable is a bit smaller. So then in the Poisson we have 1, 2, or more offspring, but for the Bernoulli we have only 0 or 1. Yeah. And because we have some space here with the small Sn term, we can play a bit around and really obtain that we make the probability of failure in the Poisson world a bit smaller. So that this still holds with sufficiently high probability that we can do this coupling for such a long time, so that we are sure that either we have hit the level n to the power b plus delta, or we are at 0. And yeah, just to say, one has to be really careful here, because one only can allow oneself this little O of Sn error terms here, yeah? Because we want to control this here to this probability Sn plus some smaller order terms. Okay, and now we have this. So we have this sum of Poisson random variables, and yeah, they have this gives us then the offspring distribution of each individual is a mixed Poisson with this random variable y inside, and the offspring mean is 1 plus Sn, because we assume that the expectation of y is 1. And the offspring variance can be by the total law of variance also obtained, and it converges to rho squared. So this upper branching process has as a survival probability 2Sn divided by rho squared, and that it's not survives forever, but just hits this level n to the power of b plus delta. This is the same probability plus some smaller order terms. Okay, for the coupling from below, we use a different approach. So there we consider the parents one after the other, and ask how many offspring they have. And so let psi I be the number of offspring of the first say beneficial individual in generation G. And this number is, again, binomially distributed, because we have n individuals that we ask if the parent is of beneficial type. And this is the probability with which this parent is chosen. And now if we have already done this for j-1 beneficial parents, and we assume that they have altogether k k offspring, then the j's beneficial individual, what is the distribution of its offspring number? It's n minus k, because for k children we already know what are the parents, and the probability to choose this j's parent is now yj divided by this sum here, because only this the offspring of these parents are only left. And if this number is much smaller than b to the power of n to the power of b plus delta, which is much more smaller than the square root of n, we can write here instead this expression, and divide here not by the smaller sum, but by the total sum, and make only the probability smaller. So the only thing what we now want to replace is this sum here, because for all this makes the offspring distribution still dependent. But here we have again the law of large number, or the central limit theorem working, and we can approximate this sum here by n plus some smaller order terms with sufficiently high probability. So now the offspring distribution of the j's parent is can be lower bounded by a binomial random variables with this parameter and this probability. And yeah, one can also show that this lower bounding Gordon-Watson process has a probability, this reaches with probability 2Sn plus divided by rho squared plus some smaller order terms, the level n to the power of b plus delta. Okay, now we have reached the level n to the power of b plus delta, and now we want to go in fact to fixation, but first we go to the level epsilon times n. And yeah, to show this is, so if we have reached this level n to the power of b plus delta, then we have already a quite strong exponential increase of these fit individuals. And what we do then is that we estimate the variance that can accumulate in a single generation, and we show that in fact this variance, these fluctuations, are not strong enough to perturb this exponential increase so much that we can go to 0 before reaching the level epsilon times n with high probability. Okay, and then we have reached the level epsilon times n, and then then of course it's clear that we with very high probabilities and also will reach this level n. But to show this, we use a backward approach, and this backward approach then Anton will explain, I think, after the break. And yeah, it's clear that if we have reached already this high level, then the probability that if we start far away from in the future, that there is none, and then we are again in this equilibrium situation, then the probability that none of these individuals will be of the beneficial type is very small. Okay, because this the number of lines in the equilibrium ASG is large in n. Yeah. Okay, it's some power of n, and therefore we have many individuals, and that they all will not hit this these beneficial parents. The probability for this is very small. Okay. Now we have a break, I think.
Thank you very much, Cornelia and Anton. So we will have a break, and before we can already have some questions.
We don't understand you.
Cornelia, do you hear us?
Ah, no, sorry. No.
Okay.
Yeah.
So maybe there are questions already. So you can always write questions to the chat, or you can unmute yourself. I don't see everybody. There is a sort of, so right now there don't seem to be questions. So I suggest that we have a break, a small break, and reconvene 5 past 5.